So students, what we have learned from an intrinsic semiconductor is that for thermal agitation, we can create electron-hole pairs in an intrinsic semiconductor. But remember one thing, that for an intrinsic semiconductor, the number of electrons will be equals to the number of holes. Now, if we want to increase the conductivity of this semiconductor material, we have to introduce some impurities intentionally inside the semiconductor crystal. And remember one thing, that this process to introduce the defects or to introduce the impurities inside the semiconductor crystal is known as doping, and it is purely an intentional method of introducing impurities into a pure semiconductor or an intrinsic semiconductor. So what we have learned, that an intrinsic semiconductor with some intentional addition of impurity atoms will create an extrinsic semiconductor. So impurity plus an intrinsic material is equals to an extrinsic material. The impurities which are added to this intrinsic material is known as the dopant materials, or the atoms which are introduced inside the intrinsic semiconductor to make it an extrinsic material are the dopant atoms. And the pure semiconductor which have turned into an extrinsic material is the doped material. So an extrinsic semiconductor is a doped semiconductor where we have introduced the dopant atoms. Now the question just comes into play, that what materials or which atoms are used as the dopant atoms. As the elemental semiconductor such as a silicon or a germanium has a 4 valency electrons in its outer orbits, that is, these are the group 4 elements in the periodic table. So for introducing the impurity atoms inside this silicon or germanium material, we have to take group 3 elements or group 5 elements. Now, what are the group 3 elements which can be introduced as the dopant atoms? The dopant atoms which can be introduced from group 3 column are boron, aluminium, and for group 5 atoms they can be phosphorus, arsenic, antimony. Now let's check out what will happen if we introduce a group 5 atom inside a silicon structure. Let's consider this picture. Let this phosphorus atom is introduced inside the silicon structure, and as you can see that every silicon structure or every silicon atom has 4 valence electrons. So every covalent bond shared with these 2 silicon atoms have a field bond. But as per this phosphorus atom is introduced, now a phosphorus atom has, as you know, it has 5 electrons in its outermost orbit, or it has 5 valence electrons. So what will happen? 4 valence electrons will be shared by this silicon atom and the covalent bonds are filled. Now the extra electron will be in anywhere inside the silicon crystal structure, and this electron can be treated as a free electron inside this semiconductor structure, and this is the way we can create a free electron inside this semiconductor crystal. Now, as I have introduced one single atom of phosphorus inside this silicon structure, we have one free electron. If we introduce a number of phosphorus atoms as 10 to the power 10 atoms per centimeter cube of this silicon crystal, then what will happen? We have 10 to the power 10 number of free electrons inside this semiconductor crystal, and as a result the silicon structure or the semiconductor crystal has a majority carrier of electrons or majority carrier of these free electrons, and this type of semiconductor results in an N-type semiconductor or a negative type semiconductor. So this is the creation of n-type semiconductor or a negative type semiconductor, as because electron is the free carrier or electron is the majority carrier in this silicon structure. And you have to remember one thing here, that what is the purpose of this phosphorus atom inside this silicon structure. Now phosphorus, whenever it is outside this silicon structure, it is in a neutral state, as because every atom will be in a neutral state, as because the number of protons will be equals to the number of electrons inside their atomic structure. Now as the phosphorus atom is introduced here inside the silicon structure, it actually donates its fifth electron or its extra electron to the silicon structure. So this phosphorus atom can be regarded as a donor atom, as because it donates an electron to the silicon structure, and then this phosphorus atom will be a positively charged ion, as because it was initially neutral, and now when it donates an electron to the silicon structure, it will be a positively charged donor ion. So here the phosphorus can be regarded as the donor type of impurity, right? Now let's consider the case for another type of dopant atom, that is, let us introduce a group 3 element inside the silicon structure, and for an example I have taken an aluminium atom. An aluminium atom is introduced inside this silicon structure, and what will happen? Now as you know that an aluminium atom has only 3 valence electrons. So the 3 valence electrons are introduced here, and this bond, typically for an example, this bond will behave as an incomplete bond or a weak bond, as because here an electron is absent, as because the aluminium has only 3 valence electrons. So this absence of electron can be treated as a positive charge inside the aluminium structure or inside this whole silicon structure, and for a result, as an absence of electron means a lesser energy level, so any electron from any adjacent bond can be moved into this deficit amount of energy state or this type of bond, and as a result this is known as a hole, a positive charge. So now when this electron jumps to this vacant position, the vacancy will be created here. You can see that the vacancy is shifted from this bond to that bond, and as a result a positive charge is transferred inside the silicon structure. So this positive charge can be treated as a free positive charge, and this is how a hole is created inside the silicon structure. Again the question arises that what is the purpose of aluminium, or what is the contribution of aluminium inside this semiconductor crystal? As you can see that actually the aluminium atom has received an electron from any other adjacent covalent bonds of the rest of the silicon structure. So the aluminium atom can be treated as an acceptor type of dopant or an acceptor atom, and as because again here the similar things will appear, that aluminium whenever it is outside the silicon structure, it was charge neutral. Now when this aluminium is introduced inside the semiconductor structure, it actually accepts an electron from any other adjacent bonds, and it becomes a negatively charged ion. So an aluminium will be regarded as an acceptor type of impurity inside this silicon structure, and it becomes a negatively charged acceptor ion. Now as you can see that here we have created a positive charge while we have introduced a single atom of aluminium inside the silicon structure, and if the doping concentration is again 10 to the power 10 per centimeter cube, then 10 to the power 10 number of positive charges or 10 to the power 10 number of holes will be created inside this silicon crystal, and this is how we can create a p-type or a positive type semiconductor. So now let's move on to show the energy band diagrams for a p-type and an n-type semiconductor right in this video.